Alright class, let's do another practice session to make sure you are getting a lot of practice for spectroscopy. The problems I'm about to do, you have a copy of all of them. Make sure you do this problem before you watch this video. Alright, let's do it. So the first one, again, I give you a formula. It's really nice when I give you the formula because formula can help you and give you a lot of information. So when I look at this formula has 7 carbon. So we talked about this before. Number of carbon times 2 plus 2. That would be 7 times 2, 14. That would be 16. Again, on the exam, use a calculator. Don't do math in your head because the simplest math on the exam, you can mess up. Alright, so I would expect 16 hydrogen if I had nothing but single bond. But what do I have here? I have 14 hydrogen. So what does that mean? That means I lost 2 hydrogen. 214 hydrogen. So there is a double bond, there is a ring, there is something like that in this compound. Most likely a double bond, but we're not going to rule anything out. So far so good? Okay, so I know I don't have any benzene ring and I will only have 1 double bond or 1 ring. Now I'm going to look at the IR. When I look at the IR, like we talked about this before, what you don't see is just as good as what you see, right? I look at the IR and the first thing that I go, oh, that means there is no OH. That's great. Then I know the oxygen here in the formula is not the OH. And then I go, okay, look at this. I like this a lot. There is a carbonyl group right here. Okay. And that's also great because that would account for the oxygen. It will also account for the 2 hydrogen that we're missing. Okay. That's pretty good. You gave me a lot of information. Now we're going to go to Proton Nmr. Again, this is carbon NMR. We're not going to look at the carbon NMR, but I just wanted you to know what a carbon NMR looks like. The proton NMR is what we are after. Now, what I'm going to do, I'm going to label the peak A, B, C from left to right. Now, remember what we talked about again. For proton NMR, when you get a proton NMR, there are 3 things I want you to pay attention to. Chemical shifts, integration, spin splitting. Those 3 things are going to help you. Now, if I come over here, so I have a peak over here that is about 2.5. So it's downfield. What did we talk about? We said that if a hydrogen that is attached to a carbon, if that carbon is attached to a carbonyl, that makes it to be around 2.5 ppm, right? Okay, so probably these 2 hydrogen are attached to a carbon that is attached to a carbonyl. Again, it's not directly attached to an oxygen. If it was directly attached to an oxygen, it would be more downfield, around 4 ppm, but this is 2.5 ppm, so it's probably CH2 attached to a carbon that is CH2 is attached to a carbonyl. So far so good? Okay. So the hydrogen are attached to a carbon and a carbon is attached to a carbonyl. So far so good. And then what did I say is CH2? I said it's CH2 because integration is 2. Alright. Whoa, look at this one. I have a singlet at around 1.2, yeah. ppm. That's CH. But I have the integration is 9 hydrogen. Wow. The integration is 9 hydrogen. One of the possibilities, the more likely possibilities, is that I could have 3 CH3s that are equivalent to each other. Okay? Now, what does the spin splitting is telling me? So 9 hydrogen, probably is likely that I have 3 CH3s that are equivalent to each other. Now is a singlet. So what that means is they are next to a carbon that has no hydrogen, right? The adjacent atom has no hydrogen. Okay, that's pretty good. Now I'm going to come over here. Here I have 3 hydrogen, so maybe I have a CH3, and then it has a triplet. What does a triplet mean? That means the adjacent carbon had how many hydrogen? It had 2, n plus 1 rule, right? The adjacent carbon had 2 hydrogen, 2 plus 1 is 3, I get a triplet. Okay. That sounds good. So these are the pieces that I have. These are the pieces that I have. Now, if you look over here, you go, okay, so here we said this is A. The hydrogen are attached to a carbon, they attached to a carbonyl. That's why I have, it's about 2.5 ppm. I have 2 hydrogen. Here, 9H, that's crazy. Probably I have 3 CH3s. They're attached to a carbon that has no hydrogen. Now, over here, we said we have a CH3. So here's my CH3 that is attached, probably is attached to a CH2 because it's a triplet. You guys are good so far? Okay. Now, let's look over here. Peak A, what is the splitting on this one? It's a quartet, right? So if this is a quartet, that means this is next to a carbon that has 3 hydrogen, right? N plus 1 rule, 3 plus 1 is 4. Since I almost messed up, let's go over this again. So this one right here is a quartet. That means the adjacent carbon had 3 hydrogen. 3 plus 1 would be 4. I have a quartet. Could that be that this is my A peak? That makes sense. So here is a CH3 that is next to a CH2. That's why I have a triplet. And this CH2 is attached to a CH3. That's why we have a quartet. So these two are connected to each other. These two are connected to each other. Yeah, not bad. So the splitting helps. You know, the other piece of information that really helps? Carbons. Count those carbons. That really, really helps. Counting the carbons, because carbons do not grow on trees. You have to account for every carbon and don't lose any carbon. So right now, if I have this, then I would have 1, 2, 3, 4, 5, 6 carbons, okay? Because this is the same as this one. So I have 6 carbons. There is 1 more carbon to account for. But also remember that these are probably next to a carbon that has no hydrogen. So if a carbon has no hydrogen, it wouldn't show up on the proton NMR because the proton, the hydrogen is what's showing up. So how could I put this together? Well, how about this? So this is what we do know. What we do know is that we have a carbonyl that is attached to a CH2, and we think that the CH2 is attached to a CH3, right? Because we got this part down. So this would be my A peak, and this is my C peak. That makes sense. The splitting makes sense because this is a quartet, this is a triplet. The chemical shift makes sense, okay? And I have 1, 2, 3 carbon accounted for. I have 4 carbon left. Now here, we said we have 3 CH3s that are equivalent to each other, right? And they're next to a carbon that has no hydrogen because this is singlet. That's really key. So could it be that here I have 1 carbon and then this carbon has 3 methyl attached to it? That would make sense, right? Because then all of these would be attached to the same carbon. They're equivalent to each other. And then this carbon has no hydrogen. So these would be a singlet. N plus 1 would be 1 plus 0 because this carbon has no hydrogen. So 0 plus 1 would be singular, and I got a singular right here. Yeah, that makes sense, right? Okay. Now, again, I want you to remember that this is proton NMR, so the hydrogens show up. If you have a carbon that doesn't have any hydrogen, it's not going to show up here. All right, so now what I want to do, I want to count the number of carbon, right? Because that's key. So I'm going to actually do the entire formula. Let's see how many carbon we have in here. We have 1, 2, 3, 4, 5, 6, 7. Well, that's good. And then let's see how many hydrogen we have. And then we have 1 oxygen. That's great. And again, I'm going to be old school. I'm going to count every single hydrogen to make sure I'm not missing anything. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yay! Okay. That's not bad. Everything is accounted for. That's why it gives a smiley face. Yeah? All right. Nice job. Ready for the next one? Okay, let's do the next one. Here is our next problem. Again, you have this in front of you. You have a copy of this. Make sure you do it before you watch the video. So I've given you the formula. I like it when I have the formula. I can get a lot of information out of it. So you know the drill. Number of carbon times 2 plus 2 is going to give you the number of hydrogen. So I have 7 carbon, 7 times 2 plus 2. That would be 16 hydrogen. Now I have a nitrogen. Remember, we said if you have a nitrogen, for every nitrogen you add 1. For every halogen you subtract 1. And for oxygen you do nothing. So I have 1 nitrogen. So I'm going to add 1 hydrogen to it. So I would expect 17 hydrogen if everything was single bond. So far so good? Okay. Now, how many hydrogen do I actually have? I have 9 hydrogen. So what does that mean? That means that I am missing 8 hydrogen to get 9 hydrogen at the end. So I'm missing 8 hydrogen. That's a lot of hydrogen to be missing, right? Okay. So just keep that in mind that you are missing 8 hydrogen. So far so good? All right. So I know that I have double bonds, probably a ring maybe. So I'm missing 8 hydrogen. Now I'm going to come to the IR. When I look at the IR, I go, okay, the first thing that stands out to me is this peak over here. Now this is in the same region that OH usually shows up, but this is not OH, because if it was OH is a little bit nicer, it's a broader like this, right? I go, okay, so this is the same region that OH would show up, but it's not an OH. OH is a broader peak. What is this? And plus, I don't even have oxygen in the formula. So what is this? This is NH. If you go back to the IR lecture, we said this region, NH or OH, could happen. Okay, so NH or OH, they show up in this region. Now, I know I have a nitrogen. I know I'm expecting a nitrogen, so this is an NH. Now, this is like a fork, right? Now, how many lines is there? There are 2 over here. 1, 2. What that means is this is a NH2. Okay, let's take a step back. So I know in this region, NH and OH happen. I don't have an OH because, first of all, there is no oxygen in the formula. Use the formula. And plus, OH is a broad peak like that. And so this is my NH2. And now this has a fork. It has 2 peaks over here. And that means this is a NH2. That means it has 2 hydrogen. Okay, not bad. Now this is just CH. I can't really get much information out of it. This is great. This means there is no triple bond, right? I don't have any triple bond over here. That's good to know. Again, what you don't have is as good as what you have on IR. because when you don't have, will also help you figure out what your structure is. So no triple bond. So none of these 8 missing hydrogen are from the triple bond. What else? Oh my God, there is no carbonyl. Okay, that's also good to know. Also remember, look at the formula. There is no oxygen in the formula. Okay, so there is no carbonyl, there is no triple bond. I have an NH2. Not bad. I have an NH2. I'll take that. Now, let's go to the proton NMR. This one is carbon NMR. Again, we're not going to go over the carbon NMR, but I just wanted you to know what it looks like, right? Now, this is the one we're going to go over. This is my proton NMR. That's my proton NMR. Okay, now I want you to remember this, that every time you have a proton NMR, there are 3 things you are looking for. First, chemical shift. Second, integration. Third, spin splitting. Those are the 3 things you are going to look at. Alright, let's look at our proton NMR. I'm going to label the peaks from the left to right. This is A, B, C, and D. Okay. Now, when you look at peak A and B, they are in a 6.5 to 7 ppm. We talked about this. We said if you have peaks from 6.5 to 8 ppm on a proton NMR, that means you have a benzene ring. That's very distinct. So if I have peak between 6.5 to 8 ppm, that means benzene ring. And I have that over here, so I have a benzene ring. Okay? That's a good piece of information to have. Now, remember what I said back in the days now? I said when you have a lot of hydrogens missing, benzene ring is very likely, right? Because benzene ring, that means you lose 8 hydrogen. Okay? So this says I have a benzene ring, and there we go. I'm supposed to lose 8 hydrogen when I have a benzene ring. I've already accounted for those 8 hydrogens that are missing. Now, the other piece of information that is very key is when you have a benzene ring, you look at the integration. The integration will tell you so much. Here, the integration means it's 4 hydrogen. So the integration is 4 hydrogen. If you have a 4 hydrogen integration, what does that mean? That means you have a di-substituted benzene ring. So integration really matters. So we have 4 hydrogen for those benzene ring peak, which means we have a di-substituted benzene ring, which means we have a di-substituted benzene ring. So far, so good? Okay. So we know that we have a benzene ring. That's great because we have a peak. We have 2 peaks between 6.5 to 8 ppm. So we know we have a benzene ring. We know we were missing 8 hydrogen. So those are where our 8 hydrogen went to the benzene ring. And then you look at the integration, which is really key when you have a benzene ring. And when you look at the integration is 4 hydrogen. What that means is I have a di-substituted benzene ring. Now, when you have a di-substituted benzene ring, these are the possibility. The two substituent could be para to each other. The 2 substituent could be meta to each other, or the 2 substituent could be ortho to each other. So these are our 3 options. Okay? If you remember, I said the meta and the ortho, that's harder to figure out. But the one that is very easy to figure out, and I'm expecting you to know, is the para one. When you have a para, you have a doublet of doublets. Is that what we see here? That's exactly what we see here. We see a doublets of doublet. We see 2 doublets over here. So, para is the likely likely option over here. Yeah? Okay. Again, you had a peak between 6.5 to 8 ppm, you go benzene ring. Integration 4, that means it's di-substituted. Because remember, benzene ring has 6 hydrogen. If you have 6 hydrogen, you have no substituent. If you have 5 hydrogen, you have 1 substitute, so it's mono-substituted. If you have 4 hydrogen, that means it's di-substituted. If you had 3 hydrogen here, that would be tri-substituted, right? We can count the hydrogen, 1, 2, 3, 4, right? 1, 2, 3, 4, 1, 2, 3, 4. Always count the hydrogen to convince yourself. Okay, and then if it's di-substituted, well, what's the pattern? Is it ortho, meta, or para? We know the para one. We know what to look for para, and this happens to be a para. I have 2 doublets over here. All right, so far so good. Okay, now so A and B are taken care of. They're both 4 hydrogen together. That's going to be for my para substituted benzene ring. I come over here. This peak is interesting. This peak is broad. If you remember, I said when you have NH or OH, that's when you have a broad peak on the NMR. Kind of the same idea, with the same concept as IR, right? And IR, OH, and NH also show up a little bit broader peak. Now here, the same thing. I have a broad peak on the NMR. What does that mean? That is my NH2 peak. So if you see a broad peak on an NMR, is an OH or NH2 peak. And in this case, I know I don't have any O. This is my NH2 peak. Now, what is the integration of this peak? This is really key. The integration is 2 hydrogen. So if the integration is 2 hydrogen, this is NH2 and not NH, which will confirm our IR, which told us that we have an NH2. Feels good to get confirmation, doesn't it? It does. Alright, so this is my NH2. Now, let's go to the last one. Last one is interesting. It's a peak around 2.2 ppm, and the integration is 3 hydrogen. So, I'm thinking it's probably a CH3 is a singlet, which means is next to a carbon, probably, that has, or next to an atom that has no hydrogen. So it's next to adjacent carbon, the adjacent atom has no hydrogen. That's why you get a singlet, right? Because the adjacent has no hydrogen, so then 1 plus 0 would be 1. I get a singlet. Okay. Now, this is about 2.2, and you're probably used to, like, when you see a 2.2 peak, you go, oh, that's probably next to a carbonyl. And I usually agree with you, except we have no carbonyl here. So this cannot be next to a carbonyl. If I had a carbonyl here, I go, oh, this peak is probably next to carbonyl, but I don't have a carbonyl here. Okay, but I know it's a CH3 attached to something that has no carbon. So these pieces are great. I have these pieces all together. Now, again, use the formula as much as you can. I have 7 carbon, right? I have 7 carbon. Keep that in mind. I have 7 carbon. Over here, you have 6 carbon, okay? Now, over here, you had 1 carbon. That would automatically be 7 carbon. So this carbon over here, so we said this is probably attached to a carbon with no hydrogen. This has to be one of the carbons of the benzene ring, because remember, we have 7 carbon, 6 carbon over here, and then 1 carbon already accounted for over here. So this carbon has to be one of the carbons on a benzene ring, because I can't have another carbon. I only need 7 carbon. So far so good? Okay. So now let's put it together. Let's put it together. I know I have a benzene ring. I'm going to put my benzene ring. I know it's a para substituted benzene ring. I'm going to put that. And I know on one side I have CH3 and the other one I have NH2 because the only two substituents that are show up on an IR, you have a CH3 and you have an NH2. Okay, so I'm just going to put those two together. Now, does the number of carbon and everything make sense? Let's count it. 1, 2, 3, 4, 5, 6, 7. Yeah. So I have 7 carbon, C7. How many hydrogen do I have? I have 1 nitrogen. That's great. I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes. That makes me very happy. Okay. This deserves a smiley face because everything is accounted for. Okay. Again, this carbon, we said CH3 is attached to something that has no hydrogen. And this carbon over here, it does not have any hydrogen. So this is the carbon that one is attached to. I'm going to draw a little peak so you can see. So this carbon would be this carbon over here. So far so good? Okay, not too bad. All right. Now, one thing I want to do, let's label the peaks. Again, taking a step back, I knew you had a para-substituted benzene ring, and I have only 2 substituents. I have a NH2 and I have a CH3. So those are the 2 options that I can just put in there. It's not too bad. Now, what I want to do now, I want to label it. So we know this is peak D. Does that make sense? It does make sense. It's next to a carbon that has no hydrogen because 1, 2, 3, 4 carbon already has 4 bonds here. So it's a singlet and it's a CH3. Now you see how this one, usually CH3s show up at about 1 ppm, but this one showed up at about 2.2 ppm. Now why was this one at 2.2 ppm and not as 1 ppm? The reason is because it's directly attached to a benzene ring. Is directly attached to a benzene ring. So the benzene ring, and there is a nitrogen over here too, is pulling the electrons away from those hydrogen. So it makes it to be a little bit more downfield. So this is directly attached to a benzene ring. I have a nitrogen over here. So again, these things are the electron density is getting pulled over here. So this ends up being more de-shielded. So far so good? Okay. So that makes sense. Now the nitrogen one, we talked about it. This is peak C because I had 2 hydrogen there. Now, what's going on with peak A and B? How could I label peak A and how could I label peak B? I'm going to put the hydrogens over here. Which one is A and which one is B? What do you think? I want you to think about this for a second. So we know that these 2 are the same. There's a symmetry going on here. And these 2 are the same, right? That's why I have 2 peaks. These 2 are the same. They're in the same environment. They both are both of these carbon are attached to NH3. And over here that, because again, there's a symmetry going on. Now I know these 2 are equivalent to each other. So these 2 are equivalent. And these 2 are equivalent to each other because they have exactly the same neighbors. There's a symmetry going on. Now, which one is which? I want you to think about this. Which one is which in this case? Which is this A or this is B? Is this A or this is B? Look at the chemical shift. One of them is more downfield than the other one. One of them is more downfield than the other one. I want you to look at nitrogen. Nitrogen is electronegative. Nitrogen is going to pull the electron toward itself. So we expect these 2 to be more downfield because they are near. Because they're nearby, there's an NH3 nearby that could pull the electrons this way, so then they don't have as much electron density, they can feel the magnetic field more. So I would say these 2 are A. Oh no, what did I put that as? Hold on. What did I just do that? That's also A. So these two are A, and then these two are B. Again, how did I figure out? I just look at the chemical shape. This one is more downfield. That means it's near an electronegative atom more than the other one. A are closer to this NH2 than our B's. So A would be these two peaks, and B would be these two peaks. Again, this would be 2 hydrogen, 4 hydrogen all together. This was a big one, yeah. It was the first time we had a benzene ring. How do you guys feel about it? Again, the key for a benzene ring is chemical shift and then integration, because integration will tell you how many substituent you have on a benzene ring. Okay. Nice job. Are you ready for the next one? Let's do the next one. Here is the next problem. Again, make sure you do this before you watch the video. You have a copy of all these practice problems. I give you the formula. I really like it when I have the formula. The formula can help us out. So, when you have a formula, you know that number of carbon times 2 plus 2 will give you the number of hydrogen. And in this case, I have 8 carbon. So I have 8 carbon. So 8 times 2 plus 2 would give me 18 hydrogen. So far so good. Okay, so I have 8 carbon, 8 plus, I have 8 carbon, 8 times 2 plus 2. That would be 18 hydrogen. And then I have oxygen. You don't do anything for oxygen. If you had a nitrogen, you would add 1 for each nitrogen. If you have a halogen, you would subtract 1 for every halogen. But for oxygen, you don't do anything. So if everything was single bond, we would have 18 hydrogen. But how many do we actually have? We have 16 hydrogen. So we are missing 2 hydrogen. That's not bad. Okay, so we're missing 2 hydrogen. You have a double bond or a ring. So we're missing 2 hydrogen. So far, so good. Now, let's go to the IR. What is IR tells us? I keep repeating this, that what you don't see is just as good as what you see. What I don't see here, I see no OH. And I see no ugly OH, right? So I also see no carboxylic acid. This is an important piece of information because you have 2 oxygen here. I know that 2 oxygen is not from a carboxylic acid, and I know the oxygens are not from the OH. So I see nothing here. There is no OH, there is no ugly OH, there is no carboxylic acid. This is key because I know I have 2 oxygen. Now I know I'm not looking for carboxylic acid or alcohol. Not bad. This is CH. Okay, that's not a big surprise. Doesn't help me as much. Over here, there is no triple bond. I kind of knew that because if you look at the formula, you are only missing 2 hydrogen. But it's good to confirm that we don't have a triple bond. Oh, what is this? This is a carbonyl. So I have a carbonyl. This is good because it has a double bond, right? So now I counted for the 2 hydrogen that is missing. The 2 hydrogen missing are from the carbonyl. And it accounts for 1 of the oxygen in there. So far, so good. Okay. I count for 1 of the oxygen in there. All right. So that's all the information I can get out of the IR. Now let's go to the proton NMR. This is carbon NMR. I just put it there so you see there's carbon NMR, what it looks like. But proton NMR is what we are going to look at. I am going to label the peak from left to right. A, B, C, and D. Now, this peak is the same as this one. We just zoomed it in for you guys. This one is this one. We just zoomed it in. So these are the same. These are the same. We just zoom it in so you can actually see the spin splitting much better. So these are the same. It's just zoomed in. All right. Now, remember that what you're looking at for proton NMR. Chemical shift, integration, and the splitting. That's what you are looking at. Let's look at peak A. Peak A is about 4.1 ppm. Okay. We've been over this. You know this one. If you see a peak at about 4 ppm, the first thing you're probably going to be thinking about is, oh, the carbon bonded to this hydrogen is probably directly attached to an oxygen, right? Is probably directly attached to an oxygen. So I'm going to say, and is the integration is 2. So this is a CH2 directly attached to an oxygen. So far, so good. Okay. Again, remember, when you have peaks at around 4 ppm, that means the hydrogen bonded to this carbon is probably directly attached to an oxygen. Oxygen is electronegative. This carbon is directly attached to it, so it's pulling the electron this way, and there's less electron density on this hydrogen, so they feel the magnetic field more. Unlucky about that. So integration is 2. So what I have 2 hydrogen, and then CH2 is directly attached to an oxygen. Now, splitting. This is a quartet. If you are a quartet, what does that mean about your neighbor? That means on one side is just oxygen. That means your adjacent carbon had 3 hydrogen. N+1 rule. 3 hydrogen plus 1, 4. I get a quartet. So I know from one side I have no hydrogen. It's just an oxygen. So the adjacent carbon most likely is a CH3. So, because this is my peak A, so it's down fields 4 ppm, so directly attached to an oxygen, is a quartet, which means the adjacent carbon could probably have be a CH3, 3 plus 1 is 4, so I get a quartet. So this is not bad. This is one good piece of information that we have right now. That's a big piece. Now, let's come over here. And look at this peak at 2.1 ppm. I know I have a carbonyl. So when you know you have a carbonyl and you see a peak about 2.1 ppm, what's the first thing you're going to be thinking about? The carbon bonded to this hydrogen is probably attached to the carbonyl, right? So when you see a peak at 2 ppm and you know you have a carbonyl, we know we have a carbonyl, so the first thing I think about is probably those hydrogen attached to the carbon is attached to a carbonyl. So I probably have, this is a carbonyl, and these are attached to a carbonyl, and the integration is 2 hydrogen, so I probably have a CH2 attached to a carbonyl. So far so good. So I see a singlet at 2 ppm. The first thing you think about is, that's probably that CH2 is probably attached to a carbonyl. So far so good. Okay. And again, carbonyl has no hydrogen. That is why this is a singlet, because the adjacent carbon has no hydrogen. Okay. So far great. Good job. Now, let's come to peak C. What can you tell about peak C? So this is another piece that is nice to know. Peak C, what's the integration? Is 3. So it's probably a CH3, okay? What's the splitting? Is a triplet. So a 3 hydrogen, integration is 3, so I probably have a CH3. And then the splitting is a triplet. So if I have a triplet, which means probably the neighbor was a CH2, right? Probably the neighbor was a CH2. So I have a CH3, probably the neighbor was a CH2. Okay, how you guys feel about this? Good so far? Now, so this was for B and this is for C. Let's go over this together. 3 hydrogen, integration is 3, is a CH3, and then is a triplet, so probably the neighbor had 2 hydrogen, 2 plus 1 would be 3, so you get a triplet over here. All right, we are in business. That's another good piece of information to have. Now, let's look at the last peak. Last peak, the integration is 9 and is a singlet. We've seen this before. If you have an integration of 9, what's one possibility, one likely possibility is that you have 3 methyl groups that are equivalent to each other, and because it's a singlet, it's probably attached to a carbon that has no hydrogen. Yeah? Okay. Let's review the NMR one more time. So over here, you see a peak at 4 ppm, you go, I know that if I have a peak at 4 ppm, that means the carbon that has these hydrogens is directly attached to an oxygen. So I have the integration is 2 hydrogen, I have a CH2 directly attached to an oxygen. Now this CH2 is a quartet, so it makes sense on one side, the adjacent carbon has 3 hydrogen, so you end up getting a quartet. 3 + 1 rule, this ends up showing up as a quartet. Great. I know I have a carbonyl. If you know you have a carbonyl and you end up having a peak at 2.1 ppm, probably this CH2 is attached to the carbonyl. Perfect. And again, this is no hydrogen, so you expect this to be a singlet. Now, over here, I have 3 hydrogen, so I have a CH3 is a triplet. So most likely, the neighbor is a CH2. Because again, 2 hydrogen plus 1 is 3, then this ends up being a triplet. I have this piece of information. And over here, I have 9 hydrogen, so 1 peak, 9 hydrogen, is likely that I have 3 methyl that are equivalent to each other, and they have to be attached to a carbon that has no hydrogen. So far, so good. Okay, so this is not bad. Now, let's check this out. This is, we say, is C, right? It has to be attached to a CH2. So there's CH2, CH3 attached to each other. Well, yeah, you guys see that? So that means this one right here is this one over here. And the CH2 is a CH2 over here. So this is going to be my peak C, and this is going to be my peak A. Because we have a CH2, CH3 bonded together. So most likely, these two are bonded together. These two are bonded together. Yeah? Okay. Beautiful. So we have all the pieces. You're ready to put it together. Now, what I want you to do, let's count the carbons that we have right now. I counted 4. 1, 2, 3, 4, 5, 6, 7. Okay, I didn't count these because these are already here. So again, there's one more carbon that I need, and most likely that's the carbon attached to this, because this carbon attached to this has to have no hydrogen, so it would end up being a singlet. So probably I have one carbon that has no hydrogen, and that wouldn't show up on a proton NMR, right? If you have a carbon with no hydrogen, that would not show up on a proton NMR. So let's put this together. This was a big one, but I think you guys got this down. I have a carbonyl. Do you agree? I have a carbonyl. And I have an oxygen that is attached to a CH2 and attached to a CH3. Okay? On the other side of the carbonyl, I have a CH2. Okay? I have a CH2. Oh. And then I know I have a carbon that has no hydrogen and is bonded to 3-methyl. Now, you may not get this the first time you draw it out. That's okay. You can keep drawing the molecules out and then see which one would fit all of this requirement. It's like a puzzle, yeah? You keep doing it and then until you get to the final product. Now, let's see if these make sense. So based on what I just said, basically I said this is A, this is C, this would be B, and these are my D. Before we go over to see if this would fit our proton NMR, let's count the number of carbon. 1, 2, 3, 4, 5, 6, 7, 8. Yes, that matches up. Always count those carbon. Don't lose them. And I have 2 oxygen. That's great. Now, how many hydrogen do I have? Let's count it the old school way. You ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yay! Makes me feel so much better when I count those and they're a match. Okay, big smiley face. Now, let's go over, see if the proton NMR actually backs up this structure. So, we know we had a CH2 attached to a CH3, and the CH2 was directly attached to an oxygen. So we have that over here. And then we know that we had a CH2 that was attached to a carbonyl. Now, this is a singlet, right? This is a singlet. Does this confirm that? Yes, this is my CH2. This carbon has no hydrogen, and this carbon has no hydrogen, so I expect this to be a singlet. Now, you may get other structure, but if you draw other possibilities, this peak will not end up being a singlet. Because remember, this peak B, has to be attached to two carbons that have no hydrogen. This peak is key to putting the structure together, because you may have drawn other structure. If you have drawn other structure and you were so sure that they were right, double check this one. Does peak B would be a singlet, is attached to two carbons on each side. The carbons have no hydrogen. Okay, that looks good. That looks good. Now these methyls, they also have to be attached to a carbon that has no hydrogen, because this is a singlet. So I have those attached to this. Yes, this definitely matches all the peaks. Yay! Now I'm trying to think what other structure you might have come up with and see why they wouldn't work. I wonder if some of you guys came up with a structure like this. Let me see. Okay. Now, if you come up with a structure like this, it does match the C8H16 and O2. And then there is a CH3 here. The CH2 is two CH2s. So it match up that we have two CH2s and one CH3. Would this be the correct structure? If not, why not? So if you came up with this, you were so close, we were almost there, but this wouldn't match up. And again, do the pieces first and then try to put the pieces together. Because when you look over here, the CH2 that is directly attached to an oxygen is a quartet, so it has to be attached to a methyl. So this peak has to be together. That's not the case here. This oxygen is attached to a CH2, correct, but this CH2 is attached to a carbon that has no hydrogen. So if this was our structure, this CH2 would end up being a singlet, because no hydrogen here and no hydrogen here. So this CH2 would end up being a singlet, but this CH2 is not a singlet, it's a quartet, so it has to be right here. It has to be oxygen attached to a CH2 attached to a CH3. So this would not work. This would not work. Okay, very nice job. We did a lot of practice problems. Keep doing the practice problem again. Make sure you get the concept down. But you're doing really well. Thanks for hanging in there with me. I will talk to you guys next time.